and behavior of polynomials. Before we talk about the end behavior, let's remind ourselves of some parent functions. In particular, let's look at their graphs. So y equals x squared, we know is a parabola. I'm not going to put them on the axes or do a lot of detail, but all we really need is the general shape of these. So y equals x squared is a parabola, which looks like the u. And if we had negative x squared, we talked about transformations and how that negative is going to flip the graph upside down, like that. Well, how about y equals x cubed? So there might be other things here, plus x squared or some other terms here, but my highest power is x cubed, and we'll just say it's 1x cubed. So a positive x cubed looks something like that, which means that a negative x cubed would be flipped upside down and have that general shape. And we can continue on with other powers like y equals x to the fourth. Again, we can pretend there are other things there, but it has a highest power of fourth. We call it a fourth degree. The general shape of a positive x to the fourth looks like that. And then of a negative x to the fourth would simply be upside down, of course, something along those lines. Y equals x to the fifth looks basically like an x cubed, but maybe has a couple more twists and turns in it. And you can continue on as far as you need. Now, I highly recommend that you know the parent functions, just the basic shape of all of your polynomials. Of course, in practice, we rarely go beyond fifth degree, because there's so much you can know simply by knowing the parent function. And one of those things we can know is what we call the end behavior. So the end behavior is what the graph is doing, of course, at the end of the graph. A little bit more formally, we might say something like this. As x goes to infinity, that's when we're way out on the right side of the graph, what does y do? What does y go to? Or as x goes to negative infinity, that is, if we're going this direction on the graph, that is way out to the left, what is y doing? Something along those lines. Let's look at some end behavior specifically of our polynomials. And let's start with the graph f of x equals negative x cubed plus 3x squared plus 2x minus 5. And my claim is that the highest power term with its coefficient is all we really need to know to determine the end behavior. That is, all of the other terms, they're important to get the detailed part of the graph, like finding zeros and intercepts and other things like that. But the end behavior is determined by the highest power with its coefficient. In particular, is that coefficient positive or negative? So, looking at the parent function, which is a negative x cubed, I know that the graph will look something like this, because all negative x cubes had that sort of shape. And if I know the graph, I easily know the end behavior. So as x is getting really big, as we're going this way, that is to the right on the x-axis, what's happening to y? Well, y is getting really small, if you would, or really big negative. More formally, as x goes to infinity, y is going to negative infinity. Let's look at the other side. What happens when x is approaching negative infinity? That is, if we go to the left on the graph, what's happening to the y value? Well, y is increasing without bound. That is, y is going to positive infinity. And that would be the end behavior of our graph. Let's do just a few more examples. Starting with g of x equals, let's say, x to the fourth plus 2x cubed minus 5x squared plus 11x plus 1. And when you realize that x to the fourth is the highest power, all of the other terms are basically irrelevant when we're determining end behavior. The parent function for x to the fourth has that general shape. Looks kind of like a W. And when we know the graph, we know the end behavior. So as x is getting really big, as we're going to the right, what's happening to the y value? Well, y is getting really big also. It is increasing without bound. So as x goes to infinity, y also goes to infinity. How about the other end? When x is going to negative infinity, that is, as we're going to the left on the graph, what's happened to the y value? Well, the y is increasing without bound as well. So the other end of behavior is when x goes to negative infinity, y goes to positive infinity. Let's take a look at h of x. Now let's do a fifth power. I'm just going to write a few terms. X to the fifth plus 4x squared minus 3x. If I have a fifth degree, that is my highest power is to the fifth, nothing else really matters with end behavior. If I know my parent function looks something like this. Now, it might not look perfectly like this. It might not have all of these extra twists and turns. That doesn't really matter, because it will have this sort of end behavior. As x gets really big, so does y. X goes to infinity, y goes to infinity. As x gets really big negative or really small, so does y. That is, as x goes to negative infinity, y goes to negative infinity. And we could do this with any type of polynomial. I'll do one more example for us. We'll do k is negative x to the fourth plus 7x cubed plus a bunch of other things that don't really matter, right? At least not with end behavior. Because if I know my parent function, I know k will look roughly like this. And if I know my graph, then I know my end behavior. Since k is pointing down, as x gets really big, y goes to negative infinity. And as x gets really small or really big negative, y goes to negative infinity as well. And we have the end behavior. Notice that you could extend this idea really to any graph. If you just happen to know what the function looks like, you can easily get the end behavior. So if I were to do m of x as the absolute value of x, even though this is not a polynomial, it doesn't really matter. If I know my picture, I can get the end behavior really easily. So my recommendation, know your parent functions.